so much. Appreciate that. Our next speaker is Pamela Clark from the JPL. Pam will be talking about Lunar Ice Cube, BIRCHES, and Lunar Volatiles. Take it away, Pam.
Okay. All right, so I will give you an update on where we are with this mission, a little background. We have quite an extensive team. This spacecraft bus is being built by Morehead State University, which has built several CubeSats. BUSEC is providing the propulsion. It was on that basis of the relationship between Morehead and BUSEC, and we've been talking to Morehead a long time. I've been talking to Morehead for a long time about flying an instrument. So this was the Next Step program, which is based on an SBIR, which included Morehead and BUSEC that we got funded. Originally an HEOMD program. I'm chewing on a lozenge because I have a cough, so this is so I don't cough. Sorry if it bothers you a little bit. And Goddard is building the instrument, which is based on the OSIRIS-REx OVIRS instrument, a compact version of it. I am at JPL as the science PI, and Vermont Technical College is supposed to be providing the flight software. I can have the next slide, please. We are the Lucky 13, the first deep space CubeSats. And believe me, the operational complexity of a deep space mission compared to LEO, which is where all CubeSats have flown before, is it's quite a bit more. Let's just say at least an order of magnitude. So current status is we've just had CDR. We have a Delta CDR to contend with, which involves flight software. This gets into the operational complexity routine. We have a flat sat that's basically operational that we can test subsystem simulations for all the subsystems on. The navigation trajectories, to the best of our ability, we don't know the exact release point yet from EM1. And I have two students working this summer who are absolutely wonderful from Morehead State University who are essentially developing the capability and testing it for the back end, basically the data management part, because at PDR we were told we would be delivering data to the PDS, which instead of making this strictly a tech demo, actually makes it an end-user driven requirements mission. So we need, basically we have sought additional support to contend with that because we weren't planning on doing that. That really adds a lot more effort. It's a very good thing to make the data that accessible to people. Could I have the next? And we published a paper. This is the first paper. More will come. There's supposed to be a special issue devoted to the EM1 science missions that will come out pretty soon. I'm not sure. I can't remember where. Could I have the next slide, please? Our goal is on the extreme right-hand side. Just to make it clear, our primary goal basically is to provide all the information we can on water and its components, to be able to provide more information to understand the basic transportation physics of water in its various states and components. The secondary goal is to consider all the information we have in hand from a lot of different missions that have flown before that will provide us some additional insight as to water's fate on the surface and hydroxyl's fate, involving the composition and morphology of a particular surface and its orientation relative to the poles. Tertiary, if we can get other information on other volatiles in the 1 to 4 micron band, that will be very good. And the impact of solar variations might be a possibility because we're going back to the same areas at different times of day. And if the sun is anomalous in some way, we may be able to get a handle on it. That's a possibility. Next slide. Technology goals are numerous, and as I said, we initially started out as a tech demo. BUSEC, primarily the demonstration of the BUSEC propulsion, ion propulsion drive based on iodine, and the flying of an instrument, a compact instrument that was capable of measurements related to pertaining to volatiles. Those were the two basic areas of interest that we addressed in the next step AO. There are other things that we're going to do too. I mean, a lot of things, a lot of COTS systems, including some of the ones mentioned up there. This is the first time they're flying in deep space, which makes it very exciting and also very risky. Can I have the next slide, please? I love this slide, so I stole it from Bill Farrell, but I did give him credit because it's a beautiful slide. It shows the basic things that we're contending with here in terms of the complexity of water, various sources and sinks, essentially in that equation on the upper right, and just showing the complexity. So it has to do with composition. We have mineralogy which could contribute hydroxyls. There's bound water, adsorbed water. There's water that spends very little time or more time in various locations, which has to do with temperature and illumination and other conditions as well. Meteoric infall could be a potential source. There could be interior sources as well. And we could be generating water in situ basically at the surface. A lot of different things to contend with. And we hope to provide some insight into these processes by looking at water in various forms in the 1 to 4 micron band at different times of day. So we're trying to isolate that variable. What does different time of day give us if we go back to the same areas on the surface? Could I have the next slide, please? Yeah, just to say a few more words. There's been a lot of work done, obviously, over the last decade, but two that are particularly interesting that have come out in the last couple of years, that's in the upper right-hand corner, basically more work done on LRO indicating surface ice at the South Pole, which is very interesting. Of course, we're complementary to two of the other missions, Lunar Flashlight and Lunar Map, that are flying at the same time. They're specifically looking for ice at the poles, either at the surface or buried. And what happens, where water ends up and what we see is going to be very interesting. There'll be some overlap in terms of our time at the moon. And then other work on the lower right-hand corner that indicates that there probably is a relationship between the overall exposure to solar wind. It could have some latitudinal basis. That'll mean there'll be varying degrees of darkening and therefore reflectivity, which is kind of interesting for us. Next slide, please. These are just some of the features we can look at, some of the ones that have been specifically called out over the last decade in yellow, the ones that are specifically related to water and their sources, and then other ones that are in aqua there, other parts of the spectrum, which we will also cover, that will allow us to do some confirmation. Because in the upper right-hand corner, you can see that that's a very broad feature at 3 microns, and our intention in building the instrument was to make sure that we had thorough coverage in that area, which has not normally been provided by instruments that have flown around the moon. So there's hydroxyl, there's water, there's ice, and by looking at other parts of the spectrum, we hope to be able to further isolate basically what we're looking at in that band and provide the highest spectral resolution in that part of the instrument. Could I have the next slide, please? That's a picture of the instrument. It's a fairly simple instrument. It's about this size. This size, the entire instrument. I do mean that. That includes the microcryocooler, of course, the spectrometer, the optics, and the electronics. It's about 1.6 U at this point, I think. It's hard to imagine something that tiny, but it's still fairly simple. It's a simple optics box, 2 off-axis mirrors, adjustable field stop, basically allow us to control the size of the spot on the surface, a focal plane array, H1, a Teledyne H1RG focal plane array, and the microcryocooler, which we have obtained from Ames with the Iris microcryocooler, which was designed to be very compact. It's the only microcryocooler that was designed with a very compact controller, and they're going to the next generation now. But we will provide the first deep space test of their hardware. And just over on the right-hand side, there is a little table that shows a comparison between Ralph and BIRCHES. Ralph is in the same family of instruments that OVIRS is. And there's obviously a lot of difference except for power. And the reason we have to use more power is because Ralph and OVIRS, for that matter, does not need a microcryocooler where they're going. Where we're going in lunar orbit, a very tough thermal environment, we need a microcryocooler. So that is most of that power is to supply the microcryocooler. Nevertheless, that amount of power is nothing compared to what a propulsion system needs. Fortunately, we're not having them on at the same time. But our power system is basically designed to support propulsion. They could use 100 watts of power. We're not going to give them that, but it would get us there faster. But we have some limits. So I think we're limited to about 65 or 70 watts for the propulsion system. Could I have the next slide, please? This is a picture of the Lunar Ice Cube spacecraft with all the various subsystems labeled. We have a pointer. Look at that. Okay. Ooh. Okay. So here's the BIRCHES spectrometer, solar panels from Pumpkin. I think they'll provide us with about 90 watts of power. We have the BUSEC engine. Basically, the BUSEC's about a third, BIRCHES about a third, and the rest is everything else. We have batteries and various other kinds of hardware we need here, including the JPL Iris X-band transponder and X-band patch antennas. Basically the best transponders available to communicate from deep space at this point. Could I have the next slide, please? Here's our concept of operation. Basically, we get tumped out of VM1. We detumble the most scary first couple of hours of our life, basically to make sure we know where we are. And everybody else at the same time, all 13 of us. DSN is working very hard to make this possible, by the way, because they have to communicate with a lot of folks at approximately the same time frame. Basically, over the next, our trajectory is a fairly complex trajectory involving flying out to one of the Lagrange points over the next 8 to 9 months, depending on the specific way in which we are, 10 minutes, thank you. Yeah, we're basically dumped out by M1. And then we get into lunar capture. It takes us about 2 or 3 months to get into the lunar orbit from lunar capture. This is the clever part here. So the flight dynamics folks at Goddard, which I didn't mention before, actually figure out how it is that we can minimize the delta V we require from lunar capture to our lunar orbit, which is a equatorial periapsis, nearly polar, very elliptical orbit. So that means we have relatively close coverage over the illuminated hemisphere, and it's a repeating pattern of once every lunar cycle back to the same area on the surface. Can I have the next slide, please? And we basically take, there's a lot of overlap between our observations. We actually have half-second integration intervals, which gives us some flexibility for when we might get saturated as opposed to when we're getting to the poles where we have lower signal-to-noise ratio. So we have built in a lot of flexibility in the design of the instrument. Can I have the next slide, please? Challenges. Thermal, always a challenge. The good news is about thermal, though we can't take advantage of it, that there are several SBIRs out right now in phase 2, phase B SBIRs, which are specifically working on much higher efficiency thermal components for CubeSats. That means they take up less mass and volume, which is a critical. Optics, we had to add a cover, which is actually good from the standpoint of any potential for contamination with the iodine, because we could potentially get into some situations where the sun could come directly in and destroy our optics. Human-rated vehicle, we've got some issues there because the requirements for shock and vibration and for thermal conditions are such that all of us would die. So this is being dealt with basically by the people providing the deployer, and the temperature stuff is yet to be dealt with. Or what we're going to do basically in terms of purging, for example, there isn't a written requirement at the moment. COTS subsystems, I'm going to talk a lot more about this at the focus group today. I'm going to talk about some of the special issues involving flying CubeSats that basically it's a learning curve now for the 13 of us who are working on this, and I can share some of that information. Some ways we would do things differently, some things are in process now. And the big issue, of course, is data management, because that is a fairly intensive process to deliver to a public archive, and we're leveraging everything we can to make this possible. But we're certainly going to need to leverage resources of the community to do the data analysis. I'll be very happy to deliver the experiment data records. We'll take all our resources to do that. And some of my students are working on trying to make that possible. Nave SPICE nodes. Nave SPICE has no support, so right now we can't do an ICD. A little bit of a challenge, but hopefully that'll be taken care of. Can I have the next slide, please? I'm not going to say more about that. LunaMap will be up next. You can hear more about the, basically the relationship between the 3 missions. And conclusion, some things I've already said. Basically, we're creating a tailored solution with a standard platform. And we're learning how to do that. All 13 of us are basically flying prototypes at this point. Any questions?